In this third part of the video, we will derive the rate of the mass transfer at the liquid gas interface. So this will be another quantity of interest. What we define as the rate of mass transfer at the liquid gas interface is the mass or the molar flux at Z equals Z1, okay, which will be equal to minus C dAB 1 minus XA1 dXA over dZ at Z equal Z1, and this will be equal to plus C dAB XB1 dXB over dZ at Z equals Z1. Then you will have a questions as to why the sign in here is opposite to each other, and in here we have a dXA over dZ and this one dXB over dZ. As you know that XA plus XB should be equal to 1. So if we divide this, we differentiate that one, dXA over dZ plus dXB over dZ equal to 0, then what you essentially have is that dXA over dZ should be equal to minus dXB over dZ. So if you substitute this to replace this term in here, then of course minus multiplied by minus will be equal to plus. Okay, that's very important for you to basically derive all these things yourself, so that you can understand everything and also brush up your skill in mathematical derivations. Okay, then this one, d over dz of your expressions of b, for example xb1, xb2 over xb1, z minus z1 divided by z2 minus z1 at z. Okay, let me make it more clear. This one is at z equals z1. Okay, then this will be equal to plus c dab xb1 xb1 ln xb2 xb1 multiplied by xb1 divided by x. Oh, this one is supposed to be xb2 divided by xb1 0 1 over z2 minus z1. Now you need to remember that if you ask why this term in here can become this in here, so I'll derive it in here just for you to understand everything. So this one is your expression for xb. Z minus z1 divided by z2 minus z1, right? D over dz of bz will be equal to ln b multiplied by bz. And in this particular term in here, this can be taken as b. So if you do these things, then you will get this particular term in here after substitutions of your z with z1. Okay, you need to confirm this yourself. And if we continue in here, that we will have plus c dab for z2 minus z1 ln xb2 divided by xb1. So essentially your NAZ z equals z1 will be equal to this term in here. That can also be expressed in terms of the logarithmic average. Or the term in there, we can change it to This one is, sorry, this one is not, this one is multiplications. Okay, so this one will be xb2 minus xb1 divided by xb average. So what you will have in here will be C DAB Z2 minus Z1 xb2 minus xb1 divided by xb logarithmic natural. Or we can also express this in terms of the Z2 minus Z1 multiplied by 1 minus xa2 minus 1 minus xa1 divided by xb logarithmic natural. So this will be equal to C DAB Z2 minus Z1 multiplied by xa1 minus xa2 divided by xb logarithmic natural. Okay, these equations in here have been used for experimental determination of gas diffusivities of DAB basically. Okay, and this also finds use in the field models of mass transfer. So basically, if you can get this value in here of your NAZ at Z equal Z1, as well as the concentrations of this, and then Z2 minus Z1, and all these particular mole fractions, then you can get the value of your DAB. What we meant by the field models of mass transfer is something in terms of this that illustrated in here. Okay, where in here a solid or a liquid phase shown where a gas is flowing. So the directions of the flow of the gas is in these directions. It's going up basically. Near the surface there is a slowly moving gas film. So this gas film has a boundary. Okay, it makes a boundary with the turbulent flow of a gas. Okay, the film is bounded by the surfaces Z equal. In here that will be Z equal Z1, and at this position it will be Z equal Z2. In this model it is assumed that there is a sharp transition in terms of your molar fractions or your mole fraction in here, and then where at the main fluid stream in the turbulent flow the concentration gradients are negligible. Okay, the model is physically unrealistic, but it has been used in a lot of chemical engineering problems and theories to correlate mass transfer coefficients. Okay, lastly, what we want to show before we conclude for this particular example is that your NAZ is equal to C DAB 1 minus XA dXA over dZ. Okay, then we can substitute this in terms of unknown expressions. 1 minus XA dXA over dZ, and then this means CDAB. Sorry, I need to put it in the black color to make it clear again for you. Minus C DAB. This term in here is equal to C1. Okay, minus C DAB, and then C1 is equal to minus ln K1. And so this one is equal to C1 minus C dAB is equal to minus ln 1 minus XA2 divided by 1 minus XA1, 1 divided by Z2 minus Z1. Okay, this one can be crossed over. Then it will be equal to C dAB divided by Z2 minus Z1 ln 1 minus XA2 divided by 1 minus XA1. What you can see in here is that in here everything inside is a constant. Okay, so you can see that there is no variable z that exists in your NAZ. So this is the verifications that NAZ is a constant. It's not a function of z. Okay, with this then I conclude the video for this first mass transport problem example. Okay, I hope that you can go and basically derive everything again, because for the mass transport problem normally a logarithmic natural form arises and you need to go back into to understand some of the identity and the rules for the logarithmic natural. Okay, thank you for listening.